Okay, gentlemen, we're going to take a look at rationalizing the denominator today. So a little bit of a longer video, just to kind of make sure we understand what's happening here. So first, why do we need to rationalize the denominator? It is useful next year in calculus, and we want to know how to get rid of the radicals in the bottom of the denominator. That's useful in certain problems in calculus. Just like we were trying to get rid of the negative exponents when we were doing our lesson on exponents, the same idea. Okay, so we want to multiply the denominator by a value so that it'll cancel out the radical. We kind of can adjust the denominator so that we get the same value. It's just that it looks different, just like getting a common denominator when we're adding or subtracting fractions. The same idea. Okay, so the key word here is we're multiplying. We just had a whole lesson on multiplying with radicals. We're going to apply that here today when we're dividing. So looking at this first one, I'm just going to assume all these are denominators. We'll do a couple of examples, kind of get the hang of what we're doing, and then we'll go through some real examples with fractions. So looking at the first one, this is really x to the 1/2, x to the power of 1, and the index is 2 in the radical. So that means if I wanted the radical to go away, I need another x. It has to be x to the 2/2. That's what I want it to be. So if I take radical x, I multiply it by another radical x, multiply, I get x to the 2/2, or x squared, inside a radical, inside a square root, which just comes out as an x. Right? So we're multiplying by a number so that the power of my radicand matches the index. The power of my radicand, the variable in the radicand, matches the index. That's the whole goal, and we're multiplying every time. Okay, the next one. Cube root of x, that's x to the 1/3. The power of the x is 1, and it's in a radical with an index of 3. So that means I need 2 more x's in order for it to become x to the 3/3. So if I take my cube root of x, I multiply it by a cube root of x squared. It's got to be a cube root because you need the indexes to match. So we're always going to match our index to whatever the problem gives us. But if I multiply it by x squared in a cube root, I get x to the 3/3, meaning x cubed inside a cube root, and it just becomes an x. So now we're eliminating our fraction, and I would do this to the top and bottom, right? We'll see that example down below, but I do the same thing to the top and bottom. And in this case, I'm just looking at assuming all these are their own denominators. This x to the 1/4, we're kind of seeing the pattern here. I need 3 more x's, so that means that would become x to the 4/4. So I take this 4th root of x, multiply it by the 4th root of x cubed. Got to make sure my indices match. So I get x to the 4/4, meaning x to the 4th in a radical with an index of 4, and I just get out an x. Okay, now let's see if there's more than one. What do we do with an x and a y? And what happens if there's a 2 in there? So let's look at the next two. I have a 5th root here. So that means I have x to the 2/5, power of 2 in a radical with an index of 5, and y to a power of 1 in an index of 5. So same idea, except we're just doing it twice. I need 3 more x's in order for it to become x to the 5/5, and I need 4 more y's in order for it to become y to the 5/5. That's my whole goal. Get it, the index to match the power. So I'm going to take my 5th root of x squared y and multiply it by, again, the 5th root. It's got to match x to the 3rd because I need 3 more x's, y to the 4th because I needed 4 more y's. When we multiply, we combine the inside, the radicands. I get 5th root of x to the 5th, y to the 5th, and I just get xy, right? So I'm always getting out just the base, right? Just the base. That's the goal. And I would do the same to the top and bottom. Okay, last one of this particular example. There's a 2 in there. We treat the 2 just like we did the y, okay? We treat the 2 just like we did for the y. So there's my problem, okay? It's 2 to the 1/3. Keep that in mind. It's a 2 to the 1/3. If it was a 4, that would be a 2 to the 2/3, right? You got to find out what the power is of that number. And 2 is prime, so it's 2 to the 1/3, x to the 2/3. So that means I need 2 more 2's, in other words, a 4, in order to get it to be 2 to the 3/3, right? And then I need 1 more x in order for it to become x to the 3 over 3. So again, I get my index to match, and I'm multiplying it by a 2 squared in order to get that to become 8. And we know the cube root of 8 is 2. We treat 2 just like it's a variable. And I multiply that out, I get, right, essentially it's a 4. It says, as I was saying, 2 to the cubed, x to the cubed, inside an index of 3. And that's really just cube root of 8x to the third. And I get out just a plain old 2x. Okay, so we got to be careful with our numbers. Usually the numbers is where students mess up. Okay, we're going to do a couple problems. We want to see how it happens in radicals, and then we'll give you a few problems to practice. So first, our rules of radicals say if there's a fraction inside a radical, I can split up the radical. So I do that first. We see up top, the fifth root of 1 is just going to be 1. I'll do that at the end. But for the bottom, that's an x to the power of 1 in a fifth root, so I need 4 more x's, as we saw up above. So I multiply the top and bottom by the fifth root, indexes must match, of x to the fourth. I need 4 more x's in order to get me an x to the 5 over 5. Here's my fifth root of 1 and my fifth root of x to the fourth. I didn't put the 1 in because I know it's going to come out. And there's my bottom, fifth root of x to the fifth. So my 1's on top, my x is on bottom. I got rid of the radical on the bottom. And then there's my fifth root of x to the fourth on top. That didn't change. Can't simplify that anymore. Okay, let's look at another one. Here I see I have a x to the 2 over 4, which means I need 2 more x's in order for it to cancel out. And as you can see over there, I multiplied by x squared inside a fourth root because I needed 2 more x's and I need the indices to match. 3 times the fourth root of x squared. On the bottom, I get x squared times x squared, x to the fourth inside a fourth root. Top stays the same, can't be simplified, and the bottom is my x. I'm always getting rid of the radical. It's just an x on the bottom. All right, let's look at this one, and then we'll look at D, and those will be the last two. So this is a cube root. Again, I have my radical that's of a fraction, so I can split it up. Now looking on the bottom, here's my number, 5. 5 is prime, and I have a y squared. So it's 5 to the 1/3 and y to the 2/3. That tells me I need 2 more 5s and 1 more y. Need 2 more 5s, or 25, and 1 more y. Okay, now let me undo that for a sec. Okay, now so I'm multiplying by 2 more 5s, or 5 squared, or 25, and y to the first, because I needed 1 more y inside a radical with an index of 3 on top and bottom. Right, so it's just like if it was an x. 25, the 5 is just like if it was an x. I need 2 more, so it's 5 squared, which is 25. There's my top. It's a cube root, so I have the same indices I can multiply. 12 times 25, x squared times y. And then on the bottom, I get my 25 times 5, 125. Y squared times y, y to the third, and that's built so that that'll come out as a 5y on the bottom. And on the top, 12 times 25 is 300, x squared and y. I do my little tree just to see if I can simplify the 300, because that's a big number, but it's inside a cube root. And I see I have no triples, so I cannot take anything out of that cube root. So that remains my answer right there. Okay, a little tricky with the numbers, but treat the numbers just like you would variables. Okay, last one. A little bit of an extra step here, kind of hard, because we see that first I split up my radical, as we have done a couple times now, but I see my 16 in a cube root. That possibly could be simplified. 2 times 8, 8 is 2 times 4, and that's 2 times 2. I have a group of 3 2's, and I have 1 left over 2, so I can simplify, well, the top stays the same. I can take out a 2, cube root of the 2 that's green, that's left over, and there's my x squared. So I simplified it a little bit, so now it's a little bit easier to see it. Now I have a prime number on the inside. So I have a 2 to the 1 over 3, technically. And then I have an x to the squared, so 2 to the 1 over 3, x to the 2 over 3, meaning I need 2 more 2's, or 4, and I need 1 more x. So as you can see, I multiplied by the cube root of 4x on top and bottom. And that gives me 4 times 7, 28, x in a cube root, and the bottom gives me 2. That 2 from that's in red is still there, times the cube root of 2 times 4, which is 8. X squared times x, that's x to the third. And that thing on the bottom was built to simplify to, well, the top stays the same, was built to simplify to 2 times 2x. I've made it so that it does that. 8, cube root of 8 is 2, cube root of x to the third is x. And now I just and I checked the 28, but can't break it down. 2 2s and a 7, no triples. And there's my final answer there. Okay, so if you need to re-look back at this video to take a look at some things, please do. We did a lot of examples in here, but the goal is, if I rewrite it as a fractional exponent, it's kind of easy to see how much more I need, and that's what I multiply by. I need my index to match my power. I need my index to match my power. Okay, good luck.